because we create lots of data, right? The people of the world do tons of stuff. Everything that you do in a given day that's past sort of getting up and walking around this room creates some kind of piece of data. And even in that case, if you need to use an RFID card to get to my door, you've created a little bit of piece of data right there. So this is just a sample of some of the things that us as people in the world generate in 1 minute of one day, right? 1 minute of one day, we send 500,000 photos on Snapchat, right? We do 3.6 million Google searches, right? We receive 103 million spam emails, most of which come to my inbox. But you have to also remember that this doesn't tell the whole story. Even though these seem like big numbers, each of these things is actually made up of a bunch of smaller pieces of data. So when you do a Google search, for example, you don't just do a Google search. You send your search query, you send your location so Google can give you local results. You send some information about your laptop, your hardware, so they can give you some more, some better formatted results. You send information about your browsing history so that they can give you more relevant results. And each of those requests and each of those things that's attached is one more piece of data. So by some estimates, this company Datum, we create something like 2.5 quintillion bytes of data every day. It's not always new data, right? Some of it's just a changed version of old data. But 2.5 quintillion bytes of data changes every day. And it's not just that we create a lot of data that's got people looking for different options, right? It's the kind of data that we create. Right? We store lots of personal data. When you go through KYC, for example, a company like BlockPass, you give them your passport, right? Some people know your religion. They know how much you weigh if you have a smart scale, right? They know what your relationships are if you're on Facebook. They might know your sexual orientation, how you think about politics, right? All of this data is intensely personal, and it's created a market pressure to find a better, more secure, and more private way to store it. This Cambridge Analytica situation in the US election is a perfect example. It used very private personal data from Facebook to target you and tell you what to think about yourself, right? So the market is looking for a different solution. Now, when we talk about data storage, there's two different kinds of data storage. Object stores and databases. So we'll talk first about objects. When we talk about an object store, it's files. It's stuff you're going to put in Dropbox, right? Pictures, documents, PDFs. This kind of stuff is incredibly hard to store on a blockchain because it's too big. So the first problem here is that blockchains, like Bitcoin, for example, place an upper limit on the size of one single block. In Bitcoin's case, it's 1 megabyte. No single block can be larger than a megabyte, which is quite a controversy in the blockchain space. And the reason for that is because the way blockchains are designed, if you increase the size of a block, you also increase the computational complexity of the blockchain. So it's a scalability problem. That's why you can't just make it bigger. And the limit on that block size makes it difficult to store anything larger than the block size. So if you have a 2 megabyte file, you have to split it across multiple blocks. You can't just split it across 2 blocks, you have to split it across 4 or 5. So it's difficult. The second problem with storing blob-layer objects on a blockchain could theoretically be solved by a blockchain like Ethereum, which has no maximum block size. What Ethereum does have, though, is a maximum gas limit, which is essentially it's the transaction fee that the network takes to mine its block. And so to store, for example, a movie on the Ethereum blockchain, you could do it, but it would cost you tons of money, more than $1 to $2 US per kilobyte stored, right? So it's not very cost efficient. So we move to databases. This is a little bit more in the blockchain's wheelhouse. The problem here is not cost or data size. The problem with using blockchain as a transactional database is that it's slow, right? Speed and transaction times are incredibly slow on the blockchain. So to create a single block on the Ethereum blockchain, which is the fastest stable blockchain we have right now, maybe 15 seconds, right? So imagine that you're creating a mobile messaging app, right? And your user's gone through, they've given you their name, their email address, they've chosen a password, they've hit the submit button, right? They're ready to sign up, and then they get this. And they sit there and wait and watch this for the next 15 seconds while you commit that transaction to the blockchain, create their account. It's not an ideal user experience. Another problem with using blockchains for transactional data is exactly what Regina said earlier, which is that they're immutable. You can't change anything. If you use that same blockchain to store the password, for example, they can't change their password. Now we can approximate changing our password, but it requires adding 2 extra transactions to the blockchain. So we add one transaction that says this old password is no longer valid. We add another that says here's a new password. So it's very, very inefficient. How do we solve this? We call it going off-chain. An off-chain solution, or a layer 2 solution, depending on what you think of, or depending on how you think about it, is a separate system from the blockchain that utilizes the blockchain for its transactional properties, but does the heavy lifting off the chain. So I'm going to discuss a little bit about how we solve this problem at Datum, but this is sort of a broad approach that the industry is taking as a whole. Architecturally, we have a distributed storage network with a blockchain layer that actually tracks the transactions. So everything in the Datum network is tied to what we call a Datum identity. So you can think of it as a user account, but it's essentially an Ethereum wallet. You create a wallet, you get a private key. When you want to store some data in the network, you sign that data with the user's private key, the key that belongs to that wallet. We then take that encrypted blob and set it into the storage network. But before we do that, we wrap some metadata around that encrypted blob. So we have the owner's wallet address, for example, who owns that data. We have access information, which other wallets are allowed to access that data. The size of the original data before it was encrypted, and really importantly, a hash of the original data, so that we know what it looked like. At the same time that we insert that data into the storage network, we insert that metadata into the blockchain. And this is important because the storage network is blocked. Before the data goes in, it's encrypted. So the nodes, the storage nodes, in this case, don't actually know what they're storing. All they know is we have this encrypted blob of data, and it's sitting there, and someone at some point will come and ask for it. The hash on the blockchain is what actually tells the storage network which piece of data you want to get. And so if you're a developer or a user, and you want to go retrieve that piece of data, you go ask the storage network directly. You don't ask the blockchain. The storage network takes care of that transaction by itself. And so in this way, we avoid the slowness of normal data storage network, or of storing data on the blockchain. We don't worry about the transaction times. We avoid the size limit of the blockchain because we don't care how big the data is, since it's stored on a relatively normal old school storage system. So, why then do we need a blockchain? This is the first question everyone always asks when we talk about what we're doing. So you can store this data, and you could do the hashing, and you could do that all in a centralized manner. So why is this important? We use the blockchain for its original purpose, which is as an immutable ledger. Every transaction on a piece of data is stored on the blockchain. Let's say you store an email address in a data network account, and you want to share that email address with someone. This is kind of similar to what BlockPass does in one regard. You want to share that email address with someone. The person you want to share that with can submit a request to you. You sign a new transaction saying, yes, I authorize this person to have this information. You sign it with a private key, which either you can control or you can use our app to control. And then that transaction is committed to the blockchain. But again, you don't need to wait because the storage node already knows what's happening on the blockchain. So the person requesting your email address gets access immediately to that data, but the transaction is sort of asynchronously sent back to the blockchain. So there's a complete record of what's happened at any given time. Second is accountability. Every transaction that requires a change of control is tracked. So it's essentially a chain of custody for data. That's why we use the blockchain in this situation. So this is a sort of broad overview of how a blockchain and an old school data storage solution work together. This is not necessarily the best solution, especially if you have a different use case. There are other configurations of this. For example, if you were building Dropbox and you wanted to store some pictures or some PDFs, there's a little better way to do this that's a little faster and a little more performant. But this general concept where you have, you combine the best things we've learned in the last 50 years of developing storage technology with the actual, the wheelhouse use cases of blockchain, which are accountability, transparency, and immutability. This is the future. This is what we're working toward. And by we, I don't mean just the blockchain community, even though we're a blockchain company. I mean the world at large. So yeah, that's it. I'll get some questions. Yes.
Yeah, I think you and I talked about hashes, and I didn't explain what a hash is.
Yeah.
I want to know if you could tell them
Yes.
what a hash is, explain it.
Sure, so a hash is basically a really fancy math problem. You feed in some data, you iterate an algorithm on it, and it comes back with a string that says that can only be made by running that algorithm on that piece of data. If you change one tiny piece of that piece of data and rehash it, the hash will be completely different. Right? So it's always unique.
Okay.
I've done this a couple times.
Yeah.
Any other questions?
Why are blockchains not efficient? Why does it take 7 transactions a second? How can you compare that to, say, the Visa network or credit card network?
So the Visa network specifically, this is a really common comparison. There's something like 50,000 transactions per second, right? The core difference is that Visa doesn't have to wait for other people. Visa controls everything by itself. There are private blockchains actually that approach that transaction speed. Goldman Sachs has one that does something like 40,000 transactions per second. But that's because, again, they control the whole thing. It's a blockchain in technology speak, but it's not a public blockchain. So it's like, the reason blockchains are so slow is because you have to wait on a bunch of different people, right? If I put a block up, I have to wait for the rest of the network to confirm that block. Right? So it takes some time. Bitcoin is on the order, a transaction in Bitcoin is on the order of minutes, 5 or 6 minutes per block. Ethereum is much faster, but it's still 15 seconds per transaction. There are some newer blockchain technologies out that are maybe 5 seconds, but still, it's 5 seconds for a transaction is an eon in technology.
So could we go back to the basics, the metadata?
Yes.
Where is that stored?
The metadata is stored on the blockchain. So in our specific case, we run our own blockchain that connects back to the main Ethereum blockchain for speed purposes, so that we don't need to wait on the Ethereum network. But the metadata itself is stored on the blockchain. The metadata, in many cases, is also encrypted. So if you were storing, for example, your email address, the developer using the storage network to store it can actually encrypt not just the email address of your private key, but they can encrypt the name of the key that refers to the email address. So if you looked at our blockchain, you wouldn't know actually what's there.
So you've looked at off-chain technology, right? Have you considered plasma chains?
Yeah, so we actually we use a plasma operator to transfer our token back and forth. So our storage network is funded by the token, and so we use a plasma operator to transfer that token back and forth.
Can you explain what a plasma chain is?
Yeah, so a plasma operator really simply is it's a bridge that lets you transfer a token between different blockchains. And so in our case, what happens, our DAT token is traded on the Ethereum blockchain. So what happens if you try to make a storage request in our network, we issue a plasma request. So we issue a request from our blockchain to the Ethereum blockchain that locks those tokens on the Ethereum blockchain and then uses them to make a storage request.
Great. Great. Thank you.
Thank you.
Great.
Any questions which is there?